Hello. Now we are going to continue our work in sketching graphs, and we are going to be looking at cubics. So polynomials that have a highest power on the x of a cube. So highest power of 3 on the x, or order 3 polynomial. And how we sketch these is that we are going to find the x and y intercepts, and we are also going to find the max and min. And in this case, we can only use calculus to do that. We have to use the fact that dy dx is going to be 0 at our max and min points. This is not the same function as we're going to look at, but remember, we have our dy dx is our slope function, so the slope is going to be 0, and we have a horizontal line. So the tangent to our green curve here would be horizontal, would have a slope 0 here at the bottom of the valley and up here at the top of the hill. So that's how we're using our dy dx is equal to 0 to find our max and min points. So let's dive into the question. If we have a cubic like this, and we're told it has a root of x is equal to 2, then we know from the factor theorem that we're able to rearrange this, set the root, make the root information equal to 0, and that means that we have a factor. I now know that that is a factor of my cubic. If I was not given a root, or if I was not given a factor, then I would simply sub in x is 0, then x is plus 1, then x is minus 1, then x is plus 2, then x is minus 2, until I found a value for x that made y equal to 0. Effectively, where am I crossing the x-axis to find my first root or my first factor? So now that we have our factor, we could either draw our bracket and complete the bracket to get it equal to the cubic, or we could do long division. In this case, we're going to do long division, but we could do either. So we have x minus 2, and we're going to do long division. And when we divide our linear factor into our cubic here, we'll end up with a quadratic factor up here that we can then factorize and solve to find the other roots. Set this quadratic factor equal to 0 that we're going to find, and that is going to give us our other roots. So for long division, take the highest power of what we're dividing in and divide it into the highest powered thing that we are dividing. So we have x into 2x cubed is 2x squared. Then, so we have our divide, multiply, subtract, bring down. We've done our division. Next, multiply this by our highest power here, by our x, 2x cubed, and also multiply by anything else that we're dividing in by. So we end up with minus 4x squared. Next step is subtract, which effectively just changes the signs of what we're doing. We're subtracting this line from the line above. Subtracting a negative is the same as adding. And we get 0 here, as we'd expect. And then we are going to end up with minus 4x squared. And then final step is bring down the 10x and repeat the whole cycle again. X into minus 4x squared goes in minus 4x times. And then multiply that in, and we get 4x squared, and minus 4x times minus 2 is plus 8x. Subtracting a negative is the same as adding. We get 0, and we get 2x, and bring down. And then x divided into 2x is just plus 2. Multiply that in. 2x minus 4. Subtract. And because we know that this is a factor, we knew beforehand that this was going to happen, but it's a good way to know we didn't make a mistake when we do our long division. We got a remainder of 0. So pretty confident we didn't make a mistake in that area because we got a 0 remainder from our long division. So now we have our quadratic factor. If we set this equal to 0 and solve, we should be able to find our other roots, our other x-intercepts, our other roots. I have a common factor of 2 here. I'm going to divide both sides by my common factor of 2. X squared minus 2x plus 1 is equal to 0. And immediately something jumps out at me. If I have the number in front of the x and square it, I get the number on the end. So what does that tell me? That tells me that I have perfect square. And if we can't spot that, you can get it by just doing normal factorizing. Minus 1 by minus 1 will give you plus 1, and minus 1, and plus minus 1 will give you minus 2. So you can do it by normal factorizing, but we always want to spot those perfect squares if we can. Now what does this tell us? This tells us that we have a repeated root. Repeated root. So we have a repeated root, so we have our x minus 1 is equal to 0. So that, so x is equal to 1 is a root. That means that we have a repeated root at the point 1, 0, and we also know that we have the point 2, 0 on our graph, because we already know that x is equal to 2 is a root that was given to us in the question. So we have 2 points on the graph, and we know that one of them is a repeated root. Now let's get our y-intercept. So when we cross the y-axis, we know that we are going to have x is equal to 0. All along our y-axis line, we know that x is equal to 0. So we just sub in x is equal to 0 into our original cubic. I'll write that in. So when we sub in our x is equal to 0, we end up with y is equal to minus 4. So 0 minus 4 is on our line. We also know that the constant on the end in a polynomial is going to give us the y-intercept, and you are entitled to just write that down, but reinforcing the structure of what's going on is important for being able to answer a lot of questions. These tools have to be very natural to us. Now that we have all of these points, now we need to go to our max and min. So we know that for our max and min, that we have to have dy dx is equal to 0. So we are going to get the derivative, and we can just use our power rule. So multiply by the power, subtract 1 away from the power, multiply by the power, subtract 1 away from the power, multiply by the power, subtract 1 from the power. This is effectively x to the 0, so, or you can think about it, a constant function would have a slope of 0, whichever you prefer to think of. And now we need to find where is this going to equal 0, and I have written that in incorrectly. That's dy dx, my apologies. So dy dx is equal to this. We want to know when's that equal to 0. Well, as before, I see a common factor of 2. So I'm going to divide both sides by 2 to make my factorizing easier. And when I do my factorizing, I can't actually do that one immediately in my head, but you can break that up into minus 3x minus 5x plus 5. And we can take out our common factor of 3x on x minus 1. And then to make the bracket the same, we'd have to take out minus 5. So we end up with x minus 1 in our second bracket. And whatever way you factorize is fine, but make sure you are showing your reasoning so that you are embedding that structure as well as possible in your mind, so that it's available to you under pressure in an exam. So if these two are multiplied together is equal to 0, this could be equal to 0, or this could be equal to 0, and both situations would make our equation work out. So we rearrange. 3x is equal to 5. We get x is equal to 1. And I need to do what x is equal to. So x is equal to 5 over 3. And we need to find our values for y for these points as well. So we're going to sub back into our original equation. So these are points, these are x values for our original function that should be the locations of the max and the min. We need to find those points. So I'm going to sub them back in. Subbing in these x values into our original equation, we get one of our max or min is at 1, 0, and the other one is at our 5/3 minus 8 all over, or 27. And for graphing purposes, I don't know what those numbers are at all, so I turn them into decimals. I turn them into x is 1.7-ish, and y is minus 0.3-ish, and that's good enough for my drawing. Now we need to figure out which one is max and which one is min. Now in a standard polynomial, you don't need to stress too much because the higher one is going to be the maximum, but we still need to check. So we need to get our second derivative and see whether it's greater than or less than 0 at the given values of x that we are talking about. So d2y dx squared, this is our dy dx, and always go back to your original dy dx, not any modified form. So we end up with 12x minus 16. So then what's that behavior like at our two different values of x that we found, our 5/3 and our 1? And I find, as expected, my minimum at my x is 5/3 and my maximum at x is 1. And now I draw in my key points that I found. I know that at x is 1 is going to be a maximum, and I also know that it's a repeated root. So I can now connect the dots, and I know that my general shape for a positive cubic is going to be like this. And we see how we connect the dots. Now if we go on to our situation where we're given a graph and we need to find the equation, what we're going to do is find the roots and thereby find the factors. So we cross at x is minus 3, cross at x is equal to minus 1, we cross at x is equal to 2. Those are our roots, and I also know the point 0,3 and the point 1,4 are on my line. So if I rearrange these into factors, I know if I multiply those factors together, I should get something that is connected to this cubic, but I need to be careful if it's the right one. So how do I account for the different constants I could be multiplying by? I say k times my factors. And this is the equation of my curve. So if I sub in either 0 for x, 3 for y, or x is 1 and y is 4 into this equation, it must work out, and that will allow me to get my value for k. Now, as we often use the y-intercept, in this particular case I'm going to show using the point 1,4, but 0,3, the y-intercept, will work perfectly well. If you sub in x is 0, y is 3 into this, you will get the same value for k. Now, before we sub in, there's something that should jump out about this graph that I just want to highlight. This was a positive cubic, if the one we just worked out, and we can see that this one looks flipped. So I'm expecting that the coefficient of the x cubed part is going to be negative, and we'll see if that works out. So indeed, when we work it out, we end up with k is equal to -1/2. This was me multiplying out the brackets for space reasons. I didn't show the steps, but it's just multiplying out brackets. Now to find the equation, if we were asked for it, we need to sub that in and just multiply it by these terms here. One of the checks that we can do when we've multiplied this out is I know the y-intercept of this function, this cubic, should be at 3, and I see that that does in fact work out, which is a nice little check to see that we didn't make a mistake. And that's what we need for now.